Welcome to this Unit 21. We look at volumes. It's a topic which Archimedes spearheaded, pioneered, and first of all we want to get his formula. Put the x-axis upwards so it's kind of easier to draw. And what we have is we have some sort of solid. It can be pretty general, a pretty general solid, and we want to find the volume of this solid. So what we do, and what Archimedes did, he sliced it up. So if you slice this up into slices, so here in this case we have this slice here, and we have the thickness is dx, and the area is ax. So ax is the cross-section area. Of the solid. Then the volume is now, and x maybe goes from A to B. So these are our bounds. We start from A, go to B, goes from A to B, and we have ax dx. This is the volume formula of Archimedes. Think about this as a little slice of volume, and it's very familiar to you if you make a salad. I'm actually going to fix a salad just after this presentation, and so I have a cucumber which I'm cutting. Maybe I switch to this camera here, and I want to find the volume of this cucumber. What I can do is I can just slice it into lots of different slices here, and each of these slices has a thickness dx and the area ax, and the volume of this slice is dv, and we add up all these volumes and we get the slice, we get the whole cucumber. Here a beautiful radish, very nice. I'm just cutting it a little bit and it's fresh. So that's a slice of radish, and also delicious. Thank you, Archimedes, for his beautiful formula. So let's compute the volume of a pyramid. Just 4 pieces here. A is equal to 4. And also the base length. I kind of take the same base length here. So I assume this is equal to 4. So we have here x. So that's just x squared, and so the integral goes from 0 to 4, so the volume is the integral from 0 to 4 ax dx, 0 to 4 x squared dx. So that's x cubed third going from 0 to 4, so this is 64. 64 third. And this is something which has been known for very long. You actually will, in the homework, you will do the frustrum. And this is on the Moscow papyrus, about 1800 BC. So this formula, there's a formula here which you derive from using calculus. But these guys did not know calculus, so that was even much before Archimedes. Okay, let's compute the volume of the sphere of radius. Let's take the sphere of radius 1 for simplicity. And it's important to look at this triangle here, because this gives us the radius. And this is a right angle triangle. This is 1, if this is x. By Pythagoras, this is square root of 1 minus x squared, and the slice which we have here the slice area is pi r squared, we know that. This is the area. Also Archimedes had first the area of the circle, And now we integrate, x goes from 0 to 1. So this b is equal to 1, a is equal to 0. We go from 0 to 1, integral from 0 to 1, pi times 1 minus x squared dx. Actually, I want the whole sphere. So if I take the whole sphere, then I get a is equal to minus 1. And I can just, I don't have to multiply by 2. So let's just do this here. And then we get pi x minus pi x cubed third. And then from minus 1 to 1. So we get 1 minus 1 third is 2 third times 2 is 4 third. And if we multiply, if we scale the sphere, if you make the sphere larger, then it scales with r cubed. So this gives us then the familiar formula for the volume of the sphere. That's a very beautiful derivation, single variable derivation of the volume of the sphere. And Archimedes found this formula in a different way, using the complement of the cone in a cylinder. Very beautiful argument, which I think we have seen already. Cool. So for the lemon, so we compute the volume of a lemon. So simplified, this is just, I take here just y is equal to sine x, and we rotate this sine curve around, and so here, let's just rotate this around here, so we get this slices here. Just make that yellow. Maybe I make this a little bit orange here. So we have here, let me just make a cut. Might actually put some lemon in the salad, but good. Beautiful slice of lemon. And the slice, let me just actually take a slice off here. So we have a lemon slice here. So this is the lemon slice, and the radius here is just sinus x. Now the area of the slice cos pi r squared is pi sine square x. And we integrate that up from 0 to pi. Pi sine square x. And again, the double angle formula is your friend. Just repeat that quickly. Sine square x minus cosine 2x half. Cosine square x, cosine 2x half. Double angle formulas. I always recommend to learn this and nothing else, because sine square plus cosine square is 1, cosine square minus sine square is cosine 2x. You can see all the relations from this. And also for integration, this is really handy. So we take the integral then from 0 to pi, 1 minus cosine 2x half. So this is pi times x half minus sinus 2x fourth, cosine 2x becomes sinus 2x, and then we evaluate it from 0 to pi. That goes away, and this is just an pi again, so that's actually just pi square half. Who would have thought that there's a pi square in that lemma? So it's basics. So we have two parts. We have the part above here. That's kind of the harder part. That's what we want to compute here. So in this case, we have a slice. This is dx. And the area here is 36 minus x squared. So we integrate from 0 to 6. And we have 36 minus x squared dx times pi. So this is the part, the upper part, and then we have a cylinder. Let's just take that also. So we have a minus 44, 0. The radius is 6, so it's pi 6 square dx. So that gives us a volume of a cylinder. So that's the addition. So let's just compute that quickly. In this case, it's good to just FOIL it out. So this is, let's just call this A here, this integral, and this integral we call B. So let's just look at, maybe put Archimedes here over. So what we have is, for A, we have to integrate pi, and the integral from 0 to 6, I FOIL it out, 36 squared minus 72 x plus x to the 4 dx. And then the other part, the B part, is easy. So the B part we can actually directly get. This is just 36 times 44 times pi. So that's B. And this one we have first to compute. So this is 36 squared x minus 72 x cubed third plus 6 to the 5 fifth, and equals 6. This is 36 squared, and 6 minus 72, 6 to the 3 over 3 plus 6 to the 5 over 5. And you can see 0. So that's part A. And total calculation is A. And A plus B is not. We can do it with single variable calculus. There is a very beautiful fact which is due to Pappus. So if you take any curve and we produce a tube, and the cross section of the tube is A of x, and that's x, and that's the length. Maybe we go from A to B. So if we have the integral from A to B, A of x dx, this is the volume. So Pappus realized that the same formula which we have also for which Archimedes figured out. Actually, Archimedes already knew if we are doing some things like that, right, we don't really change the volume. We are just shifting these slices around. So when we have a solid like that built by tubes, this same formula of Archimedes also works here. We just need to know the cross section at each point, and that gives us then the volume. So in this case, we know, this is pi r squared, which is pi. So the cross section is pi. And in this case, when we actually have to look at the length of that circle, the length of that circle of radius 3, right? If you look from above, so this is 3, and this donut is here, kind of going from here to here. So the length of this donut is of this center. It's also called the centroid theorem. It's very, very general, beautiful. And it's very important in differential geometry, actually in very advanced differential geometry also. And so this is Hermann-Weyl and tube methods, very powerful. So what we have is here the length of this thing. So we go A is equal to 0, B is equal to C, kind of the radius is 3, which is 6 pi. Because the radius is equal to 3, and 2 pi r is the length. So this is 6 pi is the length of the center curve. So we know that this center curve here has length 6 pi, so we have 6 pi squared. So the volume let's thank Archimedes again for this beautiful formula, and that's it for today.